Hello everyone. In the previous lecture we talked about the shortest path algorithm and how it can be used for optimization when any problem is represented in the form of a graph. We particularly discussed the Dijkstra's algorithm and how it helps to find the shortest path from a source node to all the other nodes in a graph. However, an assumption that we considered for the Dijkstra's algorithm is that it cannot deal with graphs that has negative weights. Now we may have graphs that have negative weights. For example, in computer games, some of the tasks are going to cost you your energy, while there are some tasks that is going to refill your energy. The same way in business, some tasks are going to cost you money while others are going to help you earn some money. So this way we can have a graph that represent both positive and negative weights. So if we have that kind of situation, then Bellman-Ford's algorithm is the solution to it. It's an improved version of the Dijkstra's algorithm that works for graphs with negative weights. It can also be used with graphs that have positive weights only. However, it may not be a good choice because it's computationally more expensive. So let's just get into the working of the algorithm. So in the first step, just like we did in the Dijkstra's algorithm, we'll have to associate a cost of 0 to the source and infinity as cost for all the other nodes. Secondly, we'll have to iterate through all the nodes to verify if their costs may be updated. So for n-1 times, we are checking the cost of all the nodes and we are repeating their process for n-1 times. However, in case of the Dijkstra's algorithm, we were only looking for the direct edges of a node that we have picked, but in this case we'll have to evaluate all the edges that we have in a graph in all the iterations. So for all the edges that we have in a graph, this is nested within the first for loop. And then within this for loop, we are checking if the cost of a node can be updated. So for that, we'll use the same equation. If cost of the current node that we have selected and cost of the edge uv is less than the cost of a farther node that is v, then we are going to modify its cost as the cost or distance of v is equal to the cost of u plus the cost of the edge u to v. It's the same like if we are currently at edge u and it has got a cost of 4, while the previous cost that we have associated with a node v is 16 and the cost of this edge is 3. So since 4 plus 3 is less than 16, so we are going to modify this cost value to 7, which is 4 plus 3. So each time we are checking this for all the edges of the network and the process is repeated n-1 times. So a major difference between the Bellman-Ford's algorithm and the Dijkstra's algorithm is that the Dijkstra's algorithm was only looking at the adjacent nodes of any picked node in order to see if its weights could be modified. But in case of Bellman-Ford's algorithm, we are repeating the process for all the nodes by evaluating all the possible edges and not just the adjacent nodes. So that is the main difference, and it basically helps to tackle the problem of having negative weights in a graph, because with negative weights we need more repetitions or more updation of the values in order to get to the shortest path. So let's consider if we have a graph A, B, C, D, and these are the edges that we have got, and the weights are 3, 7, 1, 8, and 2. And since we are assuming a case of graph with negative weights, so let's say these two weights are negative. So this is the graph that we are going to use for our particular case. And we'll be finding the shortest path from the source node A to all the other nodes. So as we said in the algorithm that we have to initialize the cost of A to 0 because it's the source or the starting point, and we'll initialize the cost of all the other nodes to infinity. In order to do it in a cleaner way, we'll use the grid. So the nodes that we have are A, B, C, and D. And the algorithm is going to run n-1 times, since we have 4 nodes. So n-1 is going to give us 4 minus 1 is 3. So this is the first iteration, second iteration, and third iteration. And currently we have 0 cost for node A and infinity for all the other nodes. Now let's just list all the edges, because we'll have to look at all the edges to see if the cost of a node could be updated. So the edges that we have are A to B, B to C, A to D, D to B, and then finally C to D. So we have a total of these 5 edges. So starting with node A, we'll look at edge A, B, and see if the cost of B could be modified. This edge has a weight of -3, so we'll modify the cost of B as -3, and 0 will remain the same for A. Then using this edge BC, we'll see if the cost of C could be modified. Since B has got a cost of -3, plus 7 is going to give us a cost of 4, so we'll modify C from infinity to 4. Then the next edge is A to D. D also had the cost of infinity, so using this edge we can modify it to 2. Then the next edge is D to B. D has a cost of 2, and this has got a weight of 8, so 2 plus 8 is going to make it 10, while B already has a cost of -3, so it's not going to be updated. The only edge remaining in the current iteration is CD. C has got a value of 4. 4 minus 1 is going to give us 3, while the current value of D is 2, which is already smaller, so it's not going to be modified. So we are done with the first iteration, and you might have observed the difference that we have updated all the costs using all the edges in the first iteration, and we are going to do so for the rest of the 2 iterations as well. So A is going to remain 0 because we haven't got any end link to A that would modify its weight, and using the edge AB, this cost is going to remain as -3, and the same way all the other weights are also not going to modify. So this is the end of the second iteration, and in the third also we are going to get the same weights, and with that our algorithm is going to end. The problem that we considered over here was relatively simpler, in which the weights got adjusted in the first iteration, so the other operations were not required. We may have a check for that in order to save on computations by seeing that if the costs from one iteration to the next are not modifying, we may not need to get to the end of all the iterations. So it may get settled down before n-1 iterations, however, at maximum it's going to take n-1 iterations. So that's how Bellman-Ford's algorithm can be used to evaluate the cost of nodes in case when the graph has negative weights. Bellman-Ford's algorithm also has an assumption, and that assumption is that the graph is not having negative cycles. A negative cycle in a graph is the one in which if we go through that particular cycle, let's say we have this cycle of A to B, B to C, and then back from C to A, and let's say there are some other nodes as well, but this graph has this particular cycle where the cost of this may be -6, it may be 5, and it may be -2. So the net cost of this loop is negative. That's what we mean by negative cycles, that if you iterate through this loop, it gives you a net negative cost. That is -6 minus 2 plus 5 is going to give us -3. This is the net cost of this cycle, which is negative, so it's a negative cycle. If a graph has even one of such negative cycles, then Bellman-Ford's algorithm cannot be applied. In fact, that graph does not have the best shortest path. We may find the shortest path, but that may not be the best or the optimum value. And even if we continue with this algorithm for infinite number of times, still the weights are going to keep on reducing, because each time you go through this cycle, the weights are going to be reduced further. We are going to talk about this further and compare it with the Dijkstra's algorithm in the next video. Before we move on, let's calculate the computational cost of Bellman-Ford's algorithm. So its computational cost is going to be n, because the first loop is n minus 1 times, so since this is constant we can ignore this part, and then we have a nested loop that is v times. So considering a complete graph, we are going to have n into n minus 1 divided by 2 edges. Again, if we just ignore the constant part, the edges are going to be n square. So we are looking at n square edges for n number of nodes. So basically it's n into n square, which is going to give us the worst time complexity of the Bellman-Ford's algorithm as n cube. So it's quite obvious that this algorithm is computationally more expensive, and that's because, as we discussed, that graphs with negative weights takes more iterations in order for the costs of their nodes to settle down. And to do so, this algorithm keeps on checking all the nodes from all the possible edges, and the process is repeated n times, so therefore this is the worst time complexity. Thank you.